So the question is, how do reactions happen? And the rate constant, which we've said before, is like the most important part of a reaction in terms of predicting how fast it goes. How does it change with temperature? Because we know reactions speed up. We know that when we cook in an oven, the higher the temperature, the faster the reaction. So let's explore this part now. So here's a generic reaction. So we got two reactants, A and B, and they turn into C and D. Now it turns out that A and B don't just disappear in a puff of smoke and form C and D. They have to actually collide. And so if A and B are molecules, they must physically hit each other. And they can't just sort of bump into each other gently. They've got to suffer a massive head-on, extremely dangerous collision with enough energy in order to react. And so we can kind of sketch this out. And so if the kinetic energy, Ke, which remember is the energy of motion, and that's 1/2 the mass times the square of the velocity, if the kinetic energy is too small, then what's going to happen is that your molecules A and B, so there's some A and here's some B, these guys are going to come up to each other and they are simply going to bounce off of each other. And this is a no reaction. Now it turns out that when molecules react in solution, they have to bump into each other maybe 1 trillion times. And only after the trillionth time do they have enough energy for something more interesting to happen. Now think of those odds, 1 in 1 trillion. So you wouldn't play the lottery. Actually, you probably shouldn't play the lottery anyway, but you wouldn't play the lottery if the odds of winning were 1 in 1 trillion, right? But if the kinetic energy is greater than a particular value, which we call the activation energy, EA, energy of activation, and actually it can be equal to or a little bit bigger than or massively bigger than. But anyway, if it's above a certain critical value, then something really cool happens. So here's my molecule of A and my molecule of B, and they are going at each other like crazy. And then what's going to happen is that these guys are going to hit each other. And when they hit each other, something amazing happens. They actually start to squish together, okay? And it's sort of A and B are commingling, their electron clouds are joining up. They're forming new bonds, they might be breaking new bonds. And what we've formed here is something called the activated complex. And this is like a coiled spring. And so this thing is going to break apart in an instant. And when it breaks apart, it's going to form 2 new molecules, C and D. And maybe it hasn't completely broken apart at this point, but we can see the ends starting to uncoalesce. And then we've got C going one direction and D going the other direction. And so I guess what we're looking at here is this is sort of a film strip. So this is time. And so at the start of the reaction, we're over here. And they come together, they smush together, they start to switch atoms, change bonds. And then they break apart and you've got the products. And so here's the activated complex, which is sometimes called the transition state. And if you think of this, this is really a state like a point of no return. On the left, you are a reactant, and on the right, you are a product. And at this point, you are basically halfway between reactants and products. To the left, you're clearly a reactant. To the right, you're clearly a product. Hey, we should probably go ahead and plot the energy diagram for this on the next slide. Let's try. So we're going to plot the energy, and what we're going to plot is not the kinetic energy, but the potential energy. And the potential energy is energy that depends on position. And so as the molecules are moving close together, their position is changing, And so we're going to plot their energy as a function of that position. So PE, and you can think of this as time. We often refer to this as RC, that is the reaction coordinate. And for a simple reaction, this might be time, or a bond length, or a bond angle. And for a more complicated reaction, it's probably not worth asking the question at this point what it is. So we start out, and energy is always measured with respect to something. So it starts out at some value, and over here on the left you've got A and B. And as the reaction takes place, A and B are getting closer and closer together. Their electron clouds repel, and boy, they're hating life right now. We're squeezing them together. We've got that coiled spring, we've pressed it down, and all of a sudden then we've got the transition state. So we've got the point where things snap, bonds break, new bonds make, and so all of a sudden the energy actually starts to drop, and eventually we're done, and we've got our products C and D. If we go ahead and we measure the amount of energy it takes to squeeze the reactants together until they hit this transition state, okay, this is this energy difference here between where we start as reactants and on the vertical axis here where the transition state takes place. And this is our energy of activation, E sub A. And so the bigger this is, the more energy has to be put in to get the reaction to go through the transition state and turn reactants into products. And the smaller this is, the easier it is. So this is critical to understanding how fast the reaction is going to take place. So for a reaction to take place, the kinetic energy, the energy the molecules are flying around and colliding with, has got to be at least equal to, if not greater than, the activation energy. And so if this is the case, we see a reaction. If the kinetic energy is less than the activation energy, then what we find is that we see no reaction whatsoever. So the molecules, they come in and they squeeze together, and they don't have enough energy, so they basically just roll back down this hill and go back to being a reactant. In fact, that's a really nice analogy here. And so imagine this is a hill and you are throwing a ball, and if you throw your ball and you give it a little wimpy throw, it goes up and it rolls back down to your feet. And if you throw it a little bit harder, it comes up and comes down again. So you're throwing it with a speed, and that's related to the kinetic energy. If you throw it really hard, it might make it almost to the top before it rolls back. And if you throw it just hard enough, it will get to the top and continue on and go over. And if you throw it any harder than that, it just whizzes over the top faster and faster and goes down to the other side. And so this activation energy here represents a barrier. The bigger it is, the harder the molecules have to be thrown at each other to react. The smaller it is, the easier it is. Okay, so here's a couple of diagrams I just quickly sketched. There's really two kinds of potential energy reaction coordinate diagrams here. So R's the reactant, TS is transition state, P is product. This is potential energy, energy of a function of position, reaction coordinate, time, extent of reaction, bond length, whatever you want to think it is. EA is the activation energy, and so the reactants have to collide with enough energy, they make it over the barrier, and they go down to the other side. And as long as their kinetic energy is bigger than their activation energy, they're going to react. Now, notice the difference between these two diagrams is the position of the products compared to the reactants. And so the reactants start out at a high energy, and the products are a low energy here. So that means that as the reaction happens, when it finally forms products, the products have got a lower energy than the reactants you started with. And so that means that the energy, normally in the form of heat, okay, there's a net loss in energy, so a net loss in heat in these reactions. And so we can say delta H is negative, energy has to be lost going from a reactant to a product. Okay, and then remember we call that an exothermic process. Okay, now the other kind of reactions are endothermic, right? And so delta H is positive. And so we have a look at these. We can see the reactants, in order to change into products, have got to go over this barrier. The height of the barrier is the activation energy. And we can see in this reaction, the reactants have lower energy than the products. So there has to be a net input of energy, normally in the form of heat. So that means that delta H increases, it's positive, it's an endothermic reaction, one that would absorb heat, feel cold if you're touching it because it's taken the heat from your hand.